Good day to you, my dear friends. Well, it's time to solve some LeetCode problems. Later today or tomorrow, for some of you, there's gonna be a contest, bi-weekly contest. So, I do not want to get too tired before that. Still, let's solve something. And let's start with this problem from a few days ago, more than a few days ago already. Our backlog is growing. Luckily, there is not much to talk about. We successfully solved this problem in two different ways, but still there are some improvements. What is the problem? Well, we have this tree and we want to find out the maximum depth of the tree. And I let me see my solutions. That was my one-liner, but it's hard to understand. Let's check this out. So it was done in two methods. See our go deeper method. It returns counter. What the hell is going on here? I hate it when I can't even understand my own code. So of course, let's draw as we usually do. Say we have this tree. We do not even care about the values. And now let's draw something like this. Take this root, we send it to our go deeper. Oh yeah, here we don't need another method at all. But it doesn't matter. So we are there, we check if we have this root at all. If we don't, we just return counter, which is at this point is 0. But if we have a root, here we create this array. We have counter +1, and also we have this. We take children of this root, so this one, and this one. And we use go deeper method again for each and every one of them. And of course, if we have a long way somewhere, we call this method again and again and again. This is gonna be equal in this case when we have 1, 2, 3, like what? 4 probably. And we take maximum value. And we also compact, because we can have nil. Do we need to compact, by the way? I'm not sure. Let me try this without compact. What's gonna happen? You see, it's very beneficial to go back to previously solved problems. So we can have a nil here theoretically, and we do not want that. For example, if this root doesn't have any children. Let's check this, by the way. Say we have an array, and in this array we have a nil, and we want to take max value from this array. What's it gonna return to us? Yeah, it returns nil. So for sure we want to have a compact here. And if we do not have any children, of course counter +1 is gonna be our new counter, and we're gonna return this. But I hate solve these problems with recursion. When it's a breadth first search, then I prefer a while loop. Something like this. No, where is my while loop? Come on. Yeah. While loop. So the same story. We have a tree. I don't know. Counter is 0. In our level array we have our first node, so this one is in the array. And if we do not have this node, then we have nil here. That's why I use compact to turn array with a nil to just an empty array. And why do I want that? Well, because I have this condition. If a level is not empty, we run this while loop, and an array with a nil is not empty because there is a nil in this array, and we want to have an empty array in this case. So that's why we have compact. Now we start our loop. Our array is not empty, we have one node, and if it's not empty, we increment our counter. Our counter is 1. So this is depth 1, level 1. Now I use reduce. I start with an empty array and we check children of node. If this node has children, we add its children to this empty array. Well, in the beginning it is empty. So in our case, we're gonna have all 3 of these nodes in our array. Now, our level array contains 3 nodes, so we are still in this loop. We increment our counter again by 1. It is 2 now. And now we check every one of these nodes if they have children. So this node has 2 children, we add them to our array. This node, it doesn't have any children, so our array remains the same. We return the same accumulator. And then this node has 1 child, we add it to the array. And this is our next array. And it's not empty. It's not empty. So our counter is 3. Again, we check all the children. If we have any, we have just 1. Our counter is 4. And this one doesn't have any children, so we return an empty array in the end. And if array is empty, we stop our while loop. Our counter is 4, we return counter. I think it's a lot more readable than a recursion. And of course there are some variations of these 2 approaches in solutions section, but for the most part they're similar. Let's check this one. Well, it is a recursion. It's very similar. But there is one solution that seemed funny to me. Again, a similar solution. There was a solution with a while loop. The first cheat, is that we can set counter in this line. Then we don't need it here. It's one improvement, if you can call it that. And then this, instead of reduce, we can just do map children, I think. And we're gonna have all these arrays of children, or empty arrays if this node doesn't have any children. don't have any children, so we want to flatten it also. Something like this. Nice, it works. Of course, I do not like flatten in the end, but it's a lot more readable than my solution with reduce. Reduce is not very readable. So I like this one. Maybe we can do, or maybe we can't, map with an exclamation mark. Not sure. No, it's not, it's never gonna end, right? Nice. And I can't tell you much more about this problem. I think this is the best approach to it. Now, another easy problem that we encountered last week. This one, it's a funny one. Minimum cost to move chips to the same position. So we have all these chips in different positions. This means that we have a what does it mean? I already forgot. Oh boy. One, two, three. Okay, it means that we have the first chip in position 2, second chip also in position 2, third chip also in position 2, this chip in position 3, this chip in position 3. So this is how this array works that we get as an input. How many moves do we need to move all the chips to one position? We want to find the minimum number of moves, and we need to draw for this for sure. I mean, there is a rule here. Let me draw some positions, doesn't matter. Some positions. 1, 2, 3, 4, 5, 6, 7, 8, doesn't matter. So we have this and this and this and this and this and this. And we have, where is it, an additional rule. When we move our chip just one position in any direction, a cost is 1 of such a move. So to move 7 this chip to 6 position gonna cost us 1. You see? But to move a chip for 2 positions, say if we want to move 7 to 5, it's gonna cost us 0. This is a rule. And what does it mean? It means that, let's say we want to move all chips to some even position, to position 4, let's say. We want to put them here. This is our goal. So for every other, for all the chips in even positions, it's gonna cost 0, because it's gonna be done with double jumps. I mean, to move both of these here is gonna be 0. in 6 we do not have anything, but we have 2 chips in 8, and to move them to 6 gonna cost us 0 because it's a jump for 2 positions, you know, and to move them here is also 0. So we do not spend anything to move all our even chips to any even position. It's free for us. But for any odd position, we want to move a chip to an even position, and it's going to cost us 1. And after that, all the next jumps are going to be free, because from 6 to get to 4 is 0. That means that every odd chip, every chip in odd position gonna cost us 1, because we want to move it to an even position, and after that it's gonna be free. That means that if we decide to move everything into any even position, then our cost is the number of chips in the odd positions, 1, 2, 3, 4, 5 in this case. If we want to move anything to, I don't know, here, odd position, then it's another way around. Everything that we have in odd position, these 5 chips, they're gonna be free. But for every chip in even position, for these 2, for 8, we're gonna pay once for every chip. First to move them to an odd position, and then to move them to the final position is gonna cost us 0. So if we choose some odd position, our cost is gonna be the number of even chips, of chips in even position. 1, 2, 3, 4, 4. So what is the minimum number of moves in this case? Well, it's 4. So the minimum number of moves is always, if we count all chips in even positions and all chips in odd positions, which one is smaller? That's our answer. So my solution was like this. We have 2 counters, we count even, we count odd, we go through our positions, and of course if position is even, we increment count even, if it's odd, we increment count odd, and then we find which one is smaller. And well, that's pretty much it, but I found a funny way of solving this problem somewhere here. No, let's call it even and odd, something like this, and it's gonna be an array 0, 0, array like this. Now let's do this operation. If our position is even, we're gonna get 0. If our position is odd, we're gonna get 1. So this line serves like double purpose. When we have an even number, we increment this element because we get 0 here. If it's an odd number, we get 1 and we increment this element. And here we just want to find like even, odd, min. Ain't it funny? Nice. And now, finally, I want to solve a problem we encountered yesterday. Yesterday we started virtual contest. We took this contest from the last page, this one. Maybe it still goes, by the way, because they gave us 24 hours to finish it. And I solved just one problem, the easy one. I want to talk about this problem because I've been thinking about it for past 20 hours, I guess. What is the problem? We have, say, 13. We want to turn 13 into numbers, from 1 to 13, and we want to sort them in lexicographical order. But we want to do that in big O of n time, and we want to use big O of 1 extra space. And I had this idea. I looked at the pattern again and again and again. If we have 13, what's it gonna be? It's gonna be 1, then it's gonna be 10, then it's gonna be 11, 12, 13, and only after that it's gonna go with 2, 3, 4, and so on until 9. Right? What if we had not 13 but 23? I'm not sure that it's gonna work, by the way. You'll see. So 23, we're gonna have 1 again, 10, the same thing, 11, 12, 13, 14. Oh yeah, it's gonna take some time. 16, 17, 18, 19. Now it's gonna be 2, then it's gonna be 20, then it's gonna be 21, 22, 23, and then it's gonna be 3, 4, 5, 6, 7, 8, 9. Right? So I noticed a pattern. I tried a lot, like 113, 200 and whatever. I tried a lot of different variations and I noticed a pattern. So first of all, let's say we do a while loop. Let's say our starting number is 1, of course. And while, well, let's not call it starting number, let's call it just num. While num is less or equal to 9, we're gonna do our loop. We're gonna have this array of results, and we're just gonna add number to results, and we're gonna increment number by 1, like this. And of course we're gonna get numbers from 1 to 9 in our results, I hope. Yeah. Now, how can we stop for a moment and add 10 and 11 and 12 and 13 here? Or not just 10, 11 and 12 and 13, but all this lot of numbers. And then after 2, add all that, Well, I think we want, after this, to do a recursion, believe it or not. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and of course we add them to array. Oh. We add them, but after adding one, we want also to add everything from 10 to 19. Here we want to add everything from 20 to 29, and so on and so forth. I mean, if we had something like a 130, I don't know, something like this, 238, then of course between these moves we also want to do this from 100 to say 109, and if it were even longer, between all these numbers you would want to add from 1000 to 1001, and of course when there is 109, we're gonna do from 1090 to 1099. I mean, it's a recursion, you see? It's hard to explain it. I spent a lot of time yesterday trying to visualize it, and still I'm not sure it's gonna work, but let's try it. Let's add another method, helper. And it's possible to do this in one method, I think. But for now, let's do it like this. And of course, we're gonna send a number here. What this number is gonna be? I'm gonna call helper here, because we want to have our 10 after our 1, our 20 after our 2. But we want all of those before 2. So we call helper on what? On our num multiplied by 10, I think. So then here we're gonna have 10. And here, believe it or not, probably we want also to again, we're gonna have a while loop. And here we don't want to have a while loop. We want just something like 9 times do. First of all, we're gonna add a number itself to results. Yeah, I think it's gonna work. So we send 10, add 10 to array, it's with add. Then we call a helper for 1000. Here our 10 turns into 11. Yeah. But we want to return immediately if our num is bigger than what? Then n, no content crease. How come it's such a late time? You're surprising me today. So we also want to send num here. Well, no. Well, yes, unfortunately we do. Oh, we need a global variable. Oh, it's the best way to fall asleep is to watch some zoos doing LeetCode stuff. Let's say we want to say send n here. Right. And also we want to break if our num is bigger than n. Something like this. Not sure what's gonna happen. Runtime error, results. We do not have such a thing. Of course we don't. Where is it? Ah, here is it. Wrong number of arguments. Where? Oh, here. Undefined local variable. Oh, come on. Of course. Fail. Too soon. Finished. Huh? Looks right. Do we have any cases here? Oh yeah, and of course we need similar condition. Here we want to break one, two. Looks nice. Let's submit. Okay. We lost 19 somewhere. So it's 10 times do. Oh, wait. 24. Right. Accepted. Ah, brilliantly solved with a recursion. And of course we can make it work with just one method. But it's gonna be uglier. In that case we want to set num here. By default it equals 1 because you want to start with 1. And our array results also we want to set here. And this is a problem because we do not want to have 0 in our array. We want to start with 1. let's call it counter equals, if num equals 1, our counter is gonna be 9, otherwise it's gonna be 10. And we're gonna do this counter times. Good, good, good. Here we want to send n. We want to send num multiplied by 10, and we want to send results. Something like this. It's not helper, it's lexical order. Cool, so it works. I just hate that we have to do this check every time we go deeper, and it's a lot of times. Oh yeah, and I'm so happy I was able to solve this, because yesterday I didn't understand this problem at all, and then I kept thinking about it more and more during the day, and I solved it in my mind without using anything. Now I tried my theory and it was correct. What a nice feeling. The only problem is I never can do this quick enough, you know. I need like a whole day and sometimes a whole night to come up with a sound theory. I hope I will get better at this. And for now, that's it, because a contest is nigh, and I want to save some energy for that. What's my rank? By the way, probably something awful. Oh yeah, well, not great, not terrible. And yesterday we're gonna try to solve a third problem from this contest. This one. Yesterday? No, tomorrow. I said yesterday. Tomorrow we're gonna try this problem. Oh. Well, thank you very much, No Condom Chris. There was a problem about nodes and nodes with children, and of course I thought about you, No Condom Chris, when I thought about all these children, but you weren't around. I'm happy that now you are here. And on this note, I'm gonna stop. I'm gonna stop. I'll see you after all the contests. Goodbye, my dear friends. Oh, we had so many dropped frames. I hoped it was watchable. Okay, I'll see ya.